Okay, so in the previous lectures, we discussed about different steps in the image acquisition process. When we consider the satellite imaging, so satellite-based imaging, uh, understand the concept. We have divided the entire steps into a the complete process into many steps. Like we discussed about how the energy source generates light. Okay, then what is the role of atmosphere? What is the role of atmosphere through which that the light or electromagnetic energy within electromagnetic spectrum pass through? Then let's say this is step A. Sorry, this is step B. So step B, A is at the energy source that generates the light that is required for the satellite-based imaging. Then step B is the role of atmosphere through which that light pass through. Okay. Then at step C, we discussed about how the energy falling at the ground surface or on the objects. So how that energy is redistributed into many components. Okay. Then further at the sensor end, when from the ground resolution cell, energy is reflected or radiated back towards the sensor. Okay. So it is sensed over here by the sensor, and then the further pixels are generated corresponding to the ground resolution cells. So if I consider this is the step D over here, so in today's discussion, we are going to discuss about what are the different steps which are there in this D section, okay, where we consider like how the sensor sense the energy coming from the ground resolution cells. What are the characteristics of different sensors? Okay, we also discuss about type of sensing system. So at the sensor end, to understand the process of sensing the energy till generation of pixels corresponding to the ground resolution cell, we have a certain important steps which we will cover in this lecture. First one is uh, that is types of sensing system. It can be called sensing or scanning system. So when we are going to discuss about types of sensing system, there we include the geometry of sensing system. We include its geometry, internal electronics. In the internal electronics, we'll discuss about the arrangement of various components which are required for generation of digital number corresponding to the energy that is received at the sensor from a ground resolution cell. Okay. Now the second part which we will discuss is that how we characterize the characteristics of scanning system. Okay. In terms of quality of data acquisition or quality of image. Okay. So if you combine if we see the step A, B, C, and D, so these four steps include a complete workflow in satellite-based imaging. And through the understanding of these 4 steps, you can derive the concept through which we generate the image, and even the based on the application, we can decide like what kind of data set is required, okay? In which particular band you require the data that needs to be processed for the certain application, okay? So to understand the step D over here, first we start with the basic concept of image formation in analog photography. So you know that in analog photography, if you recall, by using the analog camera, there is a requirement of photographic film like this, as you see in the image. Okay, and on the surface of this photographic film, there is a layer of silver halide. So this could be two types, like photographic film. So it is a layer of silver halide over polyester base, or it could be a paper based where the silver halide layer is there over the paper. Now we'll see like by in analog photography how images are acquired. Like once you switch on the camera, okay, then the reflected light is sensed, and that reflected light falls on this photographic film. So once the light falls on this photographic film, there is a internal chemical changes. You see in this figure. So in the first figure, it's a electron micrograph that is showing how the silver halide microcrystals are distributed over the photographic film. Okay? And this photographic film is used to record the images. What happens when the light falls over the photographic film that is comprised of silver halide? A chemical reaction takes place, and as you see in the second figure, the electron, this electron micrograph of it is a image, it is electron micrograph of partially developed silver halide microcrystals. So the microcrystals are rearranged, okay, and if you see these black spots, so they indicate the area on the microcrystal where information from the scene has been recorded. So based on the light falling on the film, the intensity of light, uh, the black spots are generated, okay, and they are generated on the basis of intensity of the light falling on the film. Okay. In this way, negatives are generated. So the photons react with the crystals to turn crystals into metallic silver over the photographic film. Okay. And that latent image is formed on the film, which on developing gives negative. And then after that, by chemical processing, a positive film, that is photograph, is generated. So the process is same as we discussed before. In case of briefly, we discussed about the digital camera. So what happens? Like let's say you position your analog camera over here, okay, and let's say if you click, and this is the field of view, that indicates the total area that is sensed by this camera. So what it does first, as we discussed before, let's say this is the area. So this is point A and B. Somewhere this is point A and B. what happens? The area is gridded into picture element. The area that is sensed, it is gridded into the picture element. Now light coming from the these picture elements, okay, they are sensed, they falls over this film, okay. So they falls over this film, and this there is a certain there is a chemical reactions takes place, and what happens, this metallic silver, when this light interact with the silver halide, okay, on the basis of intensity of light, okay, the metallic silver this in this color, uh, these microcrystals are arranged, okay. But see, I mean, this is an analog photograph, so we can't record it digitally as we do nowadays. So the negatives are generated, and further through the processing, uh, the photographs are generated certain through the chemical processing. If we apply the same concept, if we consider this is as a base concept to generate the photograph, and if we start considering the this base concept for the digital photograph, in case of digital photograph, in place of photographic film, we have a detector. CCD stands for charge coupled device. So this charge coupled device CCD, this is a electronic device, or electronic component that sense the energy falling on its surface, and the corresponding on the basis of amount of energy or intensity of energy that falls on the CCD surface, the equivalent electrons are generated. So it is a CCD is comprised of uh, microelectronic silicon chip, and we can see this is the phototransistors. So CCD is comprised of microelectronic silicon chip. We also call it phototransistor. When lights falls on the surface of CCD, it detects the electromagnetic energy, okay, and after that there is some internal processing within this chip, and equivalent electrons are generated, okay? So when photons falls on chip, okay, the electrons emit. So it is a kind of conversion of one form of energy into another form, and the number of electrons which are generated, they are proportional to the brightness of scene or amount of energy falling over the surface of CCD. Then obviously when electrons are generated, then there is a closed circuit. So voltage is produced, and that is proportional to the intensity of electromagnetic energy falling on the chip. So what happens? If I further elaborate this discussion, then so I start from the starting point. For the complete For the understanding of entire process from the energy source to the sensing of that energy reflected from the ground resolution cell to the sensor. Here, sun is considered as, in case of satellite-based imaging, sun is considered as an external energy source. So it generates okay. This is the energy and this is the wavelength. Lambda and this is wavelength. Okay. Now this electromagnetic energy passes through the medium and it is multiplied with the atmospheric transmission. Then further that energy reaches to the Earth's surface. And if we consider the very small area from the Earth's surface, let's say this part, and if I project it over here, it's a top view of this area. It looks like maybe there are certain houses, there are trees, okay, and many other Earth surface objects. So this energy interact with these ground features. Okay. Now that energy is redistributed into many forms, like part of energy reflected back, remaining part is either transmitted or absorbed. Okay. So on the basis of reflected energy, on the basis of reflection, there is a reflected energy component, and on the basis of absorption or transmission, that is responsible for rise of temperature. And in the Earth's surface, T 300 degree Kelvin, it is the average surface temperature that we consider to plot a graph of radiated energy versus wavelength for Earth. Okay. So there is a radiated component due to this phenomena. Like Earth average Earth surface temperature more than 0 degree Kelvin, and it is settled, it is situated at 300 degree Kelvin. So we have a two outgoing energy component. Let's say if I consider only one ground resolution cell, we also call it picture element. So again, I am shifting it over here. So this is the ground resolution cell we are considering for the further analysis. Okay. So from this ground resolution cell, if we consider the entire electromagnetic spectrum that is passes through the atmosphere, that reaches to the Earth's surface, and it is further reflected or radiated back. So we consider two types of outgoing or upwelling radiance, we call it, or outgoing energy. That could be radiated and it could be reflected. Okay, or both. So here we discuss the concept of 3 micrometer dividing line. Now, if I consider a particular band over here, let's say it's band B1 at in green band. If I consider a particular band where we have designed the sensor that is going to be sense this upwelling radiance. Okay. When I consider green band, so we have only the reflected energy component. Now see what happens when I consider this. the satellite onboard sensor, I'm just considering one sensor. Okay? And that sensor is designed for sensing the energy in band B1. That is the green band. Okay. So there is the sensor that looks towards ground resolution cell. There is a mirror over here. Okay. And what happens? See, this satellite is continuously revolving around the Earth's surface for a particular specific time. Uh, that sensor looks towards one ground resolution element. So for a for a fixed time, let's say we can say it delta t. For delta t times, one ground resolution cell is sensed by this sensor. Okay, that is designed to be sense the energy in green band. So see, from this ground resolution cell, there is a upwelling radiance available in entire electromagnetic spectrum. Though the intensity of upwelling radiance varies with respect to the its reflective, like what kind of features we have within this ground resolution cell. Okay, it all depends on the how much the energy is reflected back at a different wavelength. But for the understanding, I consider over here only green band. Now energy that is reflected back towards the sensor from the entire area, let's say this is area A, and if we consider is a square cell, then it is m cross n. So when we talk about total upwelling radiance, it goes to the medium, and we have already seen that, and we have already discussed about the effect of scattering while the sensing of upwelling radiance from the ground resolution cell. So there is a possibility, like due to scattering in the green band within the atmosphere, some atmospheric scatters also fall in the FOV at that time over here. Okay? So the total energy that is sensed by the sensor over here is combination of some of the atmospheric scatters in the green band, okay, as well as the upwelling radiance coming out from the ground resolution cell. So let's say the entire total energy that is E over here. So the total energy that is sensed that falls on this mirror. Okay? And further this mirror direct the energy at its focus over here. And here we have the charge coupled device, CCD. It could be a square in shape. Okay. So here we have a CCD. This is the surface of CCD. On the surface of CCD, the entire energy falls. Just like we discussed over here, no? Like in case of analog photography, the energy falls over the photographic film. Okay. And this film, this photographic film, if we consider one picture element, so this is made up with a silver halide crystal. Once it interacts with the light. Okay, so when it interacts with the photons, what happens? It turned into the crystal and turn crystals into metallic halide. So this silver halide crystals are turned into metallic silver color. Okay, and just see how they are arranged. So this is a electron view uh, from the electron micrograph, and this is a second view after the energy photons interacted with the silver halide. But here, what is happening? On the basis of chemical reaction, the film is changing. Okay, but in this case, what we see over here, like this is the surface of, this is one CCD, one charge coupled device, okay, that is comprised of phototransistors, silicon chip, as I said before. When light falls over the surface, uh, the total energy E, that is, if we say this N is C by lambda, where N is total photons which are falling. Okay, so this is the light that falls on the surface, and that light contains N photons. Okay. What happens over here? Right, the same CCD I am trying over here. So the CCD is a photo device, and when the light falls, the equivalent electrons are generated. And you know that the to generate the electrons or to generate the electricity, there should be a voltage difference between two end. Okay, so at two end, when light falls and there is certain internal processing, uh, due to that internal processing, a voltage difference, let's say V naught is generated. And when we have a voltage difference, then there is an electric current due to the movement of electrons. So overall, finally, what happens? A particular due to the difference, voltage difference, electric current is generated, and we measure the strength of this voltage over here. And this voltage, strength of this voltage is given by, in a particular time, how many electrons are generated. How it is dq by dt. Okay, so the number of electrons which are generated per unit time gives the strength of voltage, and this voltage will be further used for generation of pixels, that is we call DN number. Okay, so we'll discuss it later on. For the brief understanding, I have compiled the entire process over here in one particular diagram. Okay, from the generation of energy source, from the generation of electromagnetic energy from the external energy source, that is sun, it passes through the atmosphere, finally reaches to the earth surface. Okay, when now this earth surface is seen, it is continuously seen by the satellite based sensors. Okay, and these satellite based sensors divide the area that is seen by the sensors into a grid cells, and each cell is sensed for a particular time delta t. Okay, and within this delta t time, the total energy that is falling on the surface of CCD. This energy is sensed, and it is in SC by lambda. So number of photons are there, and finally, when these photons falls on the CCD, that is a photo device, a voltage due to the voltage difference is generated to allow the flow of electrons. So equivalent electrons are generated. There is a voltage difference. Due to the voltage difference, there is a closed circuit and electrons flow. Okay. Now the strength of voltage is generated on the basis of number of electrons generated per unit time, dt. Okay. And the magnitude of voltage is finally used to generate a digital number corresponding to this particular picture element or ground resolution cell. So this process that we have discussed over here in brief, we'll have an elaborate discussion in the next slides. Now, to understand the image formation in digital photogrammetry, so the working of single CCD, as I discussed before, light falls on the CCD in terms of from one picture element in terms of total energy E. Okay, that is equal to number of photons and energy within one particular photon, that is SC by lambda. Okay. Like in the previous case, we have selected wavelength in green band. Then the voltage, the corresponding voltage is generated due to this equivalent energy E. So it is an electrical charge generated proportional to amount and intensity of light, that is in terms of total energy E. Then we'll have an analog to digital conversion. This part I will discuss later on, how the analog to digital converter work. So this analog to digital converter actually convert this equivalent voltage signal into the digital number. Now in the object space, image is represented in terms of digital numbers. If we have an 8-bit image, so for the 8-bit image, we have total 0 to 255 discrete numbers in a decimal number system. We call them digital number. So these two steps, we will discuss later on. Now in the image formation, as I discussed before, the entire area that is sensed by the sensing device or scanning device, it is first divided into the grids. Okay, and as you see over here, like if we consider this area over here, and if we see the pattern of grid cell, so in a particular row, there are many grids which are arranged. We call them array. and in this array is comprised of many pixels, and they are arranged in a row. So we use many terms to represent pixel, like picture element, ground cell, ground resolution cell, etc. Okay. Then when we consider the geometry of sensing system, the geometry of sensing system with respect to the area that is to be sensed, and that is from the ground. So to understand that geometry and how one ground resolution cell is imaged, there is a terminology we use to define the geometry. We call it instantaneous field of view, IFOV. In the next slide, through the pictorial representation, I will show you how we define IFOV. Okay. Then, as I said before, the array is comprised of digital numbers which are arranged in a row. So you already know about the digital number. So just see over here. Let's say if we want to scan this particular area A that is comprised of many grids. So one way could be to scan the grid cell row-wise, like first scan this, then second, third, fourth, and fifth. Our other way could be like what I would like to tell over here. We consider the array, and let's say this array is comprised of 5 grid cells. Okay. So to understand how could be what could be the mechanism through which the sensing system capture the digital numbers corresponding to these grids. What is a mechanical rotation? What could be the way through which this array is scanned? One way could be, as you see over here, this diagram, the energy passes through the this mirror, okay, and further this energy is concentrated to the CCD surface. If you rotate the mirror, like by providing the rotation to the mirror, if let's say it is rotated to this position, now what will happen? Its focus will change. Now it is focusing to the adjacent grid to the previous one. Similarly, if you rotate further, now it is focusing to the next adjacent grid. So there is one way to understand the mechanism through which the digital numbers are captured corresponding to the cells in an array. We can provide a mechanical rotation to the optics through which energy passed through and finally it concentrated to the surface of CCD. Again, coming to this point. So how along the row these grids are captured? By providing the mechanical rotation, mechanical angular rotation to the this optics. Okay. So at for delta t time, as I said before, the focus of sensor is at this cell. Then for the next delta t, you have the rotation is already provided. Now the focus is at the second grid. Now for the next delta t, it is at the third grid and till fifth. Okay. So this could be the way to capture the digital number information for the uh, ground resolution cell. Now this is the overview of entire process. Again, like through the scanning system, how that entire area that is to be sensed is divided into the grids. Okay. Then further, the upwelling radiance which reaches to the sensor. Corresponding to that, the total energy E is estimated, and if the energy E is falling on the surface of CCD, its equivalent voltage is generated, that is calculated, and further using that the voltage magnitude, the equivalent digital number is assigned for that ground resolution cell. So as you see in the figure, this is a area segment, and various objects are present in this area segment, and it is to be sensed by the satellite based imaging. Okay, so first, what is there? Like this area segment is divided into grids. Okay. Total upwelling radiance as well as the atmospheric scatters which falls in the FOV, IFOV, instantaneous field of view of sensor. They are sensed. Okay. There is equivalent energy E that is generated corresponding to this cell. For this equivalent energy E, voltage signal V is generated, and this voltage signal E is proportional to the magnitude of energy E. And as I said before, the energy E that is equal to total number of photons in a at that particular wavelength. For all this voltage signal that is generated is proportional to the total number of photon N and the wavelength at which the upwelling radiance is analyzed. Then what happens? Corresponding to the magnitude of voltage signal V, let's say if I select this, let's say this cell has a voltage V1. So there is an analog to digital conversion. Okay. And corresponding to this V1, a equivalent digital number is generated. Now, if you see the representation over here, so each cell is represented by a decimal number. We call them a digital number, but they are stored on the disk in a binary number system. And to understand the binary number system, conversion between decimal to binary number system, we need to have how many number of bits which are required. So let's say in a decimal number system, while analog to digital conversion. After this slide, I will discuss analog to A to D conversion. So in A to D conversion, when we are going to convert analog signal into digital format, okay? So in how many segments we are dividing this analog signals, that gives us the value of unique digital number. How many unique digital numbers we want to generate corresponding to the range of analog signals. So when, let's say, if we want to generate 256, it's not 256, let's say we want to generate 230. we are dividing into 230 segments. Okay, so 230 segments means we have a digital number from 0 to 229. They are used for the representation. So when you want to convert this decimal number into binary number system, so 229, to convert 229 into binary number system, how many bits are required? Any one of you can quickly reply for this. Alok Ranjan, could you please unmute?
Yes, sir.
So as I discussed before, if we have 229, that is in a decimal number system, if you generate equivalent, like it's a binary equivalent, then how many bits are required?
Log n bits.
See, number system conversion. This is a simple problem of conversion of a number from one system to another system. Okay, so here it is a conversion of decimal number into binary number system. So 229 is given in a decimal number system. You can say it's 22910, and we want to convert it into the binary number system. Then how many bits are required? Okay. Anyone else?
So log 229.
Sir,
Base
we
2.
require 8 bits, sir.
Okay. We require
Sir,
8 bit
8
to
bits.
represent 229. We will discuss over here with reference to the analog to digital conversion. So what I said before, like the output that we get from the CCD, so I start from the grid form of area segment. So there are many picture elements. We have many cells from this area segment, and let's say if they are given a notation in terms of row and column. So this 1, 2, 3, 4. They are the row numbers, and they are the columns. And let's say 1, 2, 3, 4. This is given for the number of rows. This cell is represented by C11. Let's say C12, C13. like if we say we arrange it in terms of array, then see the first one is the row and the second one represent column. So C11, this is the first element. Then we have a C12, this is the second element. Then we have a C13, third element. Similarly, nomenclature can be given for the remaining elements. Okay. For C11, the energy is sensed E11. Similarly, for C12, and this energy is sensed at the where these energies are sensed. Anyone can respond. Like when I'm writing corresponding to the cell C11, energy sensed E11. Where it is? Where it is sensed?
Right.
It is sensed at the sensor.
At CCD.
C11, we can write it at object. Okay, at object or at the ground surface, we have a cell C11. Energy total upwelling radiance that is going outside, that is going out of C11. It goes to the medium, but finally at the sensor, the energy from the cell as well as some scatters from the atmosphere, they are sensed, and total energy E11 falls on the sensor. So we can say at sensor. Okay. The nature of energy from one form to another form, it is converted. So energy E11 is converted into the electrical signal that is recorded in terms of voltage V11 over here. And as I said before, V11 is proportional to energy E11, and energy E11 in this case, this E11 could be, it can be written as number of photons corresponding to cell C11 to SC by lambda. Lambda we have considered fixed. That's a green band, as I have started from to a case study considering the one single sensor that is designed in green band. Then we have a V12 and then we have a V11. So we can say that many voltage components are generated. For each cell we have a unique voltage component and they are represented by Vij, where I and J belong to 1 comma, you can say it's in. N we have already used over here, so we can use some other symbol over. Let's say 1 to P and J is 1 to Q, where P represent the number of rows and Q represent number of columns. Now just see this Vij. If I draw over here a line where we want to represent voltage Vij, okay. So if you want to put Vij total entire for I is equal to 1 to P and J is equal to 1 to Q. Now let's say if we analyze the objects present in this area segment, the color which I am using to paint these cells, this color represent the same type of features which are there, same type of objects which are present. Similarly, we can paint the other cells with a different color to represent if certain other objects are present. So based on the previous discussion which we had, you know that, like, let's say this entire area segment, if it is comprised of 5 major objects, okay, this area is comprised of 5 major objects. It means if you remember the spectral signature of the objects, so each object, a particular class of object has a different spectral signature, a different reflectance capability compared with the other object. If their reflectance changes object wise, it means different energy is reflected back and corresponding to the different voltages are generated. But see that corresponding to the same type of object, let's say there is vegetation, and the vegetation I have painted by 2 different sets of green color. It means there is a variation within the vegetation. There are subclasses of vegetation, and even if the same color which I have used to paint the 2 adjacent cells, we can't say that the equal energy is reflected back. There may be slightly different difference between the energy which are reflected back. Okay, so overall we can say that from each ground resolution cell, the different energy signals are reflected back, though there might be possibility they are vary with very slight difference. Okay, then corresponding to those energy signals, the voltages are generated, and from the same type of features, voltages are, the magnitude of voltages are very close. They differ only with a slight difference. So if I plot over here, let's say the mean is, first we see from this entire area element, the list of voltages Vij. First we calculate what is the minimum of Vij. Okay, then we calculate, we see the boundary, maximum of Vij. So let's say we have a generated V mean, and then we have generated V max. Within V mean and V max, we have the remaining voltages. Okay, so if you start plotting over here, if you start putting the magnitude of voltages over this voltage line, so what will happen? The voltages from same type of features, they are closely spaced. So let's say if you see this range, so 1, 2, 3, 1, 2 are the columns, and 1, 2, 4, and 5 are the rows. So we can say that this V12, V22, then further this V13, they are very close. And let's say if corresponding to the row columns 3 and 4, we have certain other objects. And then in that case, based on the reflectance of the objects which are lying in third and fourth row, or third and fourth columns, and corresponding to 1 to 5th rows. Let's say if their reflectances are more than the objects which are present in columns 1 and 2, then what will happen? Their voltages will be, let's say, 3 and 1, V3 and 2, V3 and 4, etc. So what you are analyzing over here, there are the certain voltages, they are clustered together, and the voltages which are clustered together, they represent the same type of object. Okay, so is it wise to assign a digital number directly to the each voltages? Because see, uniquely, if we want to assign a digital number, okay, each voltages, then how many unique voltages we have? Let's say Vij, P and Q. We have a unique voltages P into Q. Overall, it's a total number of cells. The entire number of cells which are present in the area, we have those number of unique voltages. And let's say if you consider the this area element 5 kilometer square, 5 kilometer square of area element, and if let's say spatial resolution is 1 meter. What do you mean by spatial resolution? If I go back over here, this is M cross M. This is a square in shape. Cell is a square in shape and size is M. M is the spatial resolution over here. Okay. If the spatial resolution is 1 meter. Okay. So what you need to do to calculate the number of cells, how many number of cells we have in this case? The M value is 1 meter. This is a square in shape and total area is 5 kilometer square. So in the grid version of this area segment, how many cells we have?
5,000.
What you need to first, this kilometer square, you need to convert into meter square, is it? So it is 5 kilometer into 5 kilometer. Convert into the meter. It is 5 into 10 to the power of 3 meter into 10 to the power of 3 meter. Okay. So what you will get? It will be 5 into 10 to the power 6 meter square divided by, it is 1 meter in a square, so it is 1 meter square. So how much cells you have? 5 into 10 to the power 6. Okay. So 5 into 10 to the power 6 unique voltages are generated, and if you want to assign a unique digital number to each voltage, then how many unique decimal numbers are required to represent each voltages? 5 into 10 to the power 6 unique decimal numbers are required. Okay, so to calculate how many bits we need, what you need to see, 2 to the power n less than 5 into 10 to the power 6 less than 2 to the power n minus 1. You need to solve this inequality. And obviously this will be more than this, very high number of bits will be required. Similarly, if you further increase the area of 5 kilometer square to 10 kilometer square, then what will happen? The 2 times the number of bits required will be 2 times. So this is not a feasible solution. Okay, because see, ultimate our goal is to uniquely represent. If we want to classify the input image into the 5 classes, only 5 classes. Okay, so why we go for assigning these voltages which vary with very slight difference? So these voltages could be given a unique digital number, single digital number, because they belong to the same class, but they vary with very slight difference. So if this is our objective, and obviously the practical scenario suggests us to go with this. But see, if you assign a digital number to each voltages, just see how much storage will be required. Very large storage will be needed, because if number of bits will increase, then yeah, they will increase. Then obviously, to store the data for one particular cell, we have more number of bits, so more space will be required. And similarly, when you go with the processing, you need to process the very volumetric data. So what can be done? This is the reason why we need to go for conversion of analog voltages to the digital equivalent. We call it analog to digital conversion. And to execute this, what we'll do, V minimum to V maximum, within which the entire voltages are they are calculated. They are lying within V minimum to V max. This range is divided into a smaller segment. Okay. What we do, let's say if we want to divide it into the this 256 segment. What we do, we divide it into the 256 segment. Even let's say we divide it into n segment. Try to write n equal segment. If we divide this V minimum to V max into n segment, n segment means n decimal numbers. Okay. So we write over here, this is start from 0, 1, 2, 3, 4 till n. Okay. So on the independent axis, we have the voltages, while on the dependent axis, that is y-axis, we have the decimal numbers, the range of decimal numbers. We call them, in the terminology of image, we call them digital numbers. So how many unique digital numbers we are generating, that depends on how many segments we are dividing the minimum to maximum voltage. We are dividing them into n segment, n equal segment, then we have a n digital numbers available to label the particular cell. Okay. And this process is called as analog to digital conversion, and this is the transfer function. The transfer function which we use okay, please wait. Can you see the shared screen?
No, sir.
Okay. So I'm giving you 5 minutes time. Kindly go through the discussion we had. Okay. And again, we resume this session after 5 minutes. Okay, now I hope you can see the shared screen.
Yes, sir.
Okay, so on the voltage line, uh, we place the voltages which are sensed, which are generated corresponding to the energy sensed from the ground element, ground resolution cell. So we have taken an example of 500 kilometer square area. So 5 kilometer square area and a spatial resolution of one cell is 1 meter. So 1 meter square. So the Vij, that is a voltage corresponding to the picture element. So how many voltages we have? 10 to the power 6. Okay. So 5 into 10 to the power 6 voltages, they are located on the voltage line. But what we do based on the SOC,
सर
yeah, please.
सर आप बोर्ड शो नहीं हो रहा है सर, मैंने रिज्वाइन किया फिर से नहीं हो रहा है.
Is it for all of you? I have shared
Yes,
the
sir.
whiteboard.
Yes, sir.
You can't see the whiteboard?
नो
No,
सर.
sir.
No, sir.
I can see the board, sir.
सर मैंने रिज्वाइन किया फिर भी नहीं शो हो रहा है.
No, if some of you can see the shared screen, then might be due to the connectivity issue we can't see. Now let me know. I have again shared the whiteboard.
नो सर, इट्स नॉट विजिबल.
सर ओपन नहीं हो रहा है.
No, okay, let me see. This whiteboard has been already shared. So I think it should be visible to your end. How many of you can't see the shared whiteboard? Okay, three of you. Okay, so three of you have raised your hand.
Sir, now it's not visible. Till
So
now
I have
it was visible.
no, fine. I have disconnected. That's why it is not. It will not be visible to you.
Okay, sir.
Let me try some other way. I have again shared the board. I hope now it is visible to you.
Yes, sir.
Okay. So with reference to the previous discussion, uh, we have voltages which are generated corresponding to the picture elements, and they are lying between two boundaries, V minimum and V max. Okay. So for the given 5 km square area with the spatial resolution of each cell 1 meter square, we have a total 5 into 10 power 6 voltages. Okay. And those voltages are placed on the voltage line that is on the independent axis, x-axis we can say over here. On the y-axis, we have the decimal numbers, like, and those decimal numbers are on the basis of how many segments we are dividing the voltage line. So let's say if we are dividing the voltage line into n segment. Okay. So if it's divided into n segment, it means on the independent axis we have a n discrete decimal number starting from 0. It is 0 to n minus 1. So 0 we have corresponding to V minimum, then 1, 2, 3, 4 till n minus 1. Okay. Now this is the process through which, this is a transfer function TF, through which we convert analog voltage signal to digital numbers which are represented in decimal number system. This is analog to digital converter. And the transfer function is plotted over here. And this is a kind of staircase function. Now Vm, V1, then we have a V2, then we have a V3. So Vm to Vn, Vm, that is a minimum voltage, to V1. Okay. The voltages which are lying between this range Vm to V1, they are assigned a same digital number. Okay. And they are given digital number 0 based on this transfer function. And see, obviously, if Vm to V1, this is very, if this difference is very narrow, so it means these voltages are from the same kind of object. Because if they are this Vm to Vn1, if this is very narrow range, we can say that these voltages are similar. So corresponding to these voltages, we have a nearly same energy signal, and it indicate like the same type of feature generate same energy. So this is not always true, because see, if we have a two different ground resolution cell, but at a particular wavelength lambda, if the reflectance is same, then in that case the digital number will be same, but there will be the difference in terms of features which are there. But this case will be in case of multi-band images. This is a single band image we are talking, and this lambda is in the green band. Okay. In the green band, if you analyze the spectral signature of various Earth surface objects, okay, the same DN number will be given in the case for two different objects if there is, let's say, the row of O1 object O1 is equal to the reflectance of object O2 at wavelength lambda. In that case, only the same distal number is assigned to two different objects. But generally, these cases are very few. We have these cases, but they are very few. Overall, we can see that in the image, if voltages are very close to each other, it means they are from the same type of object. Okay, and this is concluded on the basis of same type of object, same spectral signature, same reflectance, and same energy is radiated or reflected towards the sensor. So Vm, it means this energy, minimum energy, and this is energy E1. So there is slight difference, and they are from the same type of object. If they are from the same type of objects, then there is no problem to assign the same DN number. Okay, that's why Vm to V1 is given distal number 0. Corresponding V1 to V2, the second segment, they will be given 1 till Vm, like Vm minus 1 to Vm, they are given distal number n minus 1. Okay, and if we select n over here 8 bit, n is equal to 8. Sorry, n is a distal number. If we select n over here 256, okay, means we have a numbers which are available for assigning to the ground resolution cells. They are 0 to 255, and they are total in 256. Okay. So 256 distal numbers are available, and they are in this decimal number format. So to represent them into using the equivalent binary number system, we require 8 bit. Okay. So 256, n is equal to 256, n is equal to total segment. The equally spaced segment along the voltage line from V minimum to V max, they are n. We select n is equal to 256. So to represent them, n bit, n is, sorry, this 8 bits are required. If you further increase this number beyond 256, then we require 9 bit. So 256 to 512, we need 9 bit. Similarly, 512 to 1024, we require 10 bit. And if you increase the number of bit, means you are increasing the number of segment. So further you are dividing into, if you, let's say they are double, 256 to 1512, means the Vm to V1 is further divided into 2 unique segments. So you are interested in very finer energy differences. So to analyze the very fine energy differences, you need to increase the number of bits to represent the pixels. So is there any query? So kindly take your time to note down the entire discussion we have made over here. Specifically, you need to plot this transfer function, this 2D plot. the voltages versus digital number, and the transfer function is in the form of staircase. I'm giving you 5 minutes time to make note on this.